Welcome everyone to Knox Game Design for November 2022. So this month we're going to be talking about number systems. So number systems I'll be looking at is decimal, binary, and hexadecimal. So the reason why you may be interested in these, if you're working with a high level game development environment, you may not run into hexadecimal or binary very often, but if you're doing like assembly, low level programming, you'll probably run into it. If you're looking like at images and how a game actually works, lower level than the actual game development environment, you may run into hexadecimal, and especially if you're working on the web and you're working with color codes, or even if you're using a paint program trying to pick color codes, you may run into hexadecimal. So the first that we're going to look into is what we call decimal, or this is basically the numbers that most kids learn in elementary school. Basically 0 through 10, 1 through 10, then 10 through 20 to 100. Typically with decimal numbers, we don't pad these with leading zeros or anything, but it's the numbers that we learned in school. So basically, one thing to be aware of, which this will follow through the rest of the number systems that we look at the numbers 0s through 9s. Those are all one digit. 10 through 99, those are two digits. It's two numbers. 100 through 999 is three digits, and 1000 through 9999 is four digits. So basically, the number of numbers that you have in your number, that's a tongue twister, that's how many digits there are. So one thing to be aware of, and this might be something more like algebra, high school level, is be aware that each digit represents 10 to a certain power. So 10 to the 0 is 1, 10 to the first power is 10, anything to the first power is itself. 10 to the second power is, or 10 squared is 100, and so on. And I've got examples here up to 10 to the 6. So basically, the power that we're looking at, the exponent, is the number of zeros in your number, except for 10 to the 0. Anything to the 0 power is 1, just by rule. So we're going to look at some numbers here, and this may seem overly complicated. I try to make it color-coded, but this is another way to look at decimal numbers, how to break them out. So we got 0 through 9 over here. I don't know if my cursor is showing up. But basically, 0 through 9 is whatever that number is times 10 to the 0, which I said earlier is 1. So that number times 10 to the 0 is 1. Now, when we're looking at the two-digit numbers, like 10 is 1 times 10 to the first plus 0 times 10 to the 0. So that'd be 10 plus 0. 11 is 1 times 10 to the first, which is 10, plus 1 times 10 to the 0, which is 1. So that's 11. So I have the first digit in the number in green, and then the second digit in red. So you can see the first number in green, the one in the 10th position, is whatever that number is times 10 to the first, which is 10. So for like 58, we have 5 times 10 to the first, so that gives us 50. Then for the 8 in that second column, then that's going to be 8 times 10 to the 0. So that's going to be 50 plus 8 is 58. Or 99 is 9 times 10 to the first plus 9 times 10 to the 0, which is 90, plus 9 gives us 99. So this sounds a little bit complicated. Another way to think of it is the digit in the far right column is in the 0 position, and the green number here in the second in the leading position, that's the digit in the first position. So basically, if we look at like the three-digit number, say 256 right here, so another way to look at it is like look at the 6 first, the one here in red. So that's going to be 6 times 10 to the 0. So that's in the 0 position. Then the 5 is in the first position, so it's going to be 5 times 10 to the first. So basically, whatever position it is in, that's going to be your exponent for your 10 value. And then 2 times 10 to the second. So that's going to be 200. So 200 plus 50 plus 6 will give us 256 for this one right here. Or 777 is going to be 7 times 10 to the second plus 7 times 10 to the first plus 7 times 10 to the 0. So that's going to be 700 plus 70 plus 7. That'll give us 777. Or if we look at, I got the 4-digit numbers down here at the bottom. So we got, for instance, this one, 1,234. So that one's in the third position. So that's going to be 1 times 10 to the third. Plus, then that 2's in the second position. So that's going to be 2 times 10 to the second. And then the 3 is in the first position. So we're going, when we're talking about these positions, we're going right to left. So it's going right is 0, 1, 2, 3. So the 3 is 3 times 10 to the first. And then your 4 is going to be 4 times 10 to the 0. So that's going to be 1,000 plus 200 plus 30 plus 4 gives us 1,234. So yeah, that's probably way, seems really, like I said, complicated. But when you look at binary, it makes a lot of sense. So in binary, you just have ones and zeros, but it's kind of the same way where you're looking at the, what I was calling the digits position is now basically your bits position. So 0 and 1, that's a 1-bit number, so that's just 0 and 1. 2-bit numbers, you got 0, 0, 0, 1, 1, 0, 1, 1. So basically, the 0 and 1 is equivalent to 0, 0, and 0, 1. It just has a padded 0 at the front. So basically, those two numbers are equivalent. So if we got 3 bits, we got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. If you look at these long enough, like the way I learned a lot of this is through truth tables. If you start building truth tables with true and false, you kind of set them up like this, where you got all false to begin with. Then you add one true on the very far right side. And then you do false, true, false. And after you look at these long enough, this order kind of makes sense. And this is actually the same order. This is basically the numbers 1 through 7 right here. These are equivalent to decimal 1 through 7. So here in 4 bits, we got the same numbers. I didn't list out all the 4-bit numbers. I just put a few examples right here. But like 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, which is 0, 1, and 2. 1, 0, 0 is 4. And I'll explain how you calculate this in a minute. But these are just some examples of 4-bit numbers. So one thing to be aware of. So like on the previous slide, I was talking about 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. So we're kind of doing the same thing for binary, but it's 2's for base 2. So we got 2 to the 0 is 1, like I said earlier. Anything to the 0 power is 1. 2 to the first, anything to the first power is itself. So 2 to the first is 2. 2 to the second is 4. 2 times 2 is 4. 2 to the third is 8. So that's 2 times 2 times 2. So 2 times 2 is 4, and 4 times 2 is 8. So we got the same. We do the same thing. I just listed them up to 2 to the 13th. A lot of these numbers probably look familiar if you're into video games and things like that. 1, 2, 4, 8, 16, 32, 64, 128, 256. If you're into programming, you've probably seen 512 and 1024. I remember like the old sim memory RAM sticks were 1 megabyte was 1024 megabytes, and 2 megabytes was 2048, 2048, and 3 or 4 megabytes was 4096, and then the next one up is 8192. So, how do you convert binary to decimal? So, if you got a string of 1 and 0s, like a computer understands, how do you convert that into the decimal numbers that humans understand? So, it's the same thing that I was talking about earlier, the way that we convert numbers, but instead of using base 10, we're going to do base 2. So, we're looking at, for the first example for these 1-bit numbers, we got 0 and 1. So, that's just going to be 0 times 2 to the 0, which is 0 times 1 is 0. And then 1 is 1 times 2 to the 0. And that's 1. Anything to the 0 power is 1. So 1 times 1 is 1. So looking at these other numbers, so 0, 0, which 0, 0 and 0, 1 is the same thing, like I said earlier, as 0 and 1. It's just got a 0 padded at the front. So 0 times 2 to the first is 0. 0 times 2 is 0. Then 0 times 2 to the 0 is 0 times 1, which is also 0. So you get 0 for that. 0, 1 is 1. Looking at 1, 0. So it kind of looks like 10, but it's actually 1, 0 in binary. So 1, 0 in binary is 1 times 2 to the first, which is 1 times 2, which is 2, plus 0 times 2 to the 0, which is 1. So 0 times 1 is 0. So that's 2 plus 0 equals 2. We look at 3. We got 1 times 2 to the first, which is 1 times 2, which is 2, plus 1 times 2 to the 0, which is 1, times 1, which is 1. So we got 2 plus 1 equals 3. I didn't break it all down right here, but I can assume that people can do the calculations based on that. Just remember, anything to the first is itself, anything to the 0 is 1. So looking at some of these 3-bit numbers, let's look at 101. Skip down here. So 101 in binary, so that's 1 times 2 to the second, which is 4, plus 0 times 2 to the first, which is 0 times 2, which is 0, plus 1 times 2 to the 0, which is 1 times 1, which is 1. So we got 4 plus 0 plus 1 equals 5. So after you look at these long enough, you start realizing it's like everything in red is in the 1 position. You multiply by 1. Everything here in green, you multiply by 2. Then everything in blue, you multiply it by 4. So 111 is 4 plus 2 plus 1 is 7. 110 is 4 plus 2 plus 0, which is 4 plus 2 is 6. Look at these 4-bit numbers. It's the same thing, except this 4th position over to the left here. That's going to be 2 to the third, which is 8. So let's look at 1001. So 1 times 2 to the third is 1 times 8, which is 8. 0 times 2 to the second, 0 times 4 is 4. 0 times 2 to the first is 0 times 2, which is 0. And 1 times 2 to the 0 is 1 times 1, which is 1. So we've got 8 plus 0 plus 0 plus 1 equals 9. If we look at 1001, that's going to be 8 plus 0 plus 4. 8 plus 0 plus 2 plus 1, which is 8 plus 2 plus 1. 8 plus 3 is 11. 1111 is 8 plus 4 plus 2 plus 1, which is 8 plus 4 is 12. 12 plus 2 is 14, plus 1 is 15. So that's how you convert binary to decimal. Addition is pretty easy in binary. So just remember, it's kind of like standard addition that we learned in school with the carrying and everything. So 0 plus 0 is 0. 0 plus 1 is 1. And 1 plus 1 equals basically 1, 0. So we leave 1, then we carry a 1 to the next column over, which I have here. And so if you have 2 1s, you got 1 carried over. So if you got 1 plus 1 plus 1, that's going to leave you a 1, and then you carry another 1 over. So here's an example right here. We got 0 1 0 0, which is decimal 4, and 0 1 1 1, which is decimal 7. So if you add these two together, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 1, and 1 plus 1 is 0, then we carry a 1, then we got 0 plus 0 plus the carried 1 is 1. So that leaves us 1, 0, 1, 1, which, doing the conversion, that's 8 plus 2 plus 1 is 11. Here's another example. Basically, decimal 10 plus decimal 5, which is 1010 is 10, 0101 is 5. So all these are going to be 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 0 is 1. So what if we have, these are all 4-bit numbers, so what if we have 9 plus 7? So we got 9 in decimal, which is 1001, then we got 7, which is 0111. So we do 1 plus 1 is 0, and we carry a 1, so that's 0 plus 1 plus carried 1 equals 0, and we carry another 1. So 0 plus 1 plus carried 1 is 0. Then we carry another 1. Then we got 1 plus 0 plus the carried 1 is 0. But we still need to carry another 1, but we don't have any more places to put that 1. So that's when you basically get overflow. That's when, like, in some of these old, like NES games where you see a character wrap around to the other side of the screen. Well, nobody went in there and actually programmed it so that the character would go to the other side of the screen when he walked to the edge. That's just basically your exposition overflowing to the other side, or underflowing. You can also have underflow. I guess if you go below 0, you underflow. If you go over, like the width, which was probably 256, which is the 8-bit number, maximum. 255 is the maximum 8-bit number. So if you go to 255 and you add 1 and you got an 8-bit number, then that's going to overflow and take you back over to 0. I think there's been some misconceptions on that. But if you're looking at an 8-bit number and you got 9 plus 7, so that's, with an 8-bit number, you got 8 bits, kind of like the digits with decimal, but they're bits. So that's basically for 9 is 00001001. So it's the same number except you're padding 4 zeros at the beginning. And 7 is 00000111. So same number. It's the 4-bit number. You're just padding it with 4 zeros. And how do you know how many zeros to pad it with? Well, that's dependent by your system architecture. Basically, if you look up whatever, like programming, I guess it's either your architecture or your programming languages. Sometimes when you're defining data types, it'll tell you how many bits or how many bytes are in that number. So 1 byte equals 8 bits in most cases. I think some systems it may equal 7. It might be one way or another if it's signed or unsigned, which I'll talk a little bit about in a minute. Basically, we got these two 8-bit numbers. Same thing with the 4-bit numbers. 9 plus 7. 9 plus 7 with 4 bits, it overflows over to 0. 9 plus 7 with 8 bits, 1 byte, we'll do the same thing. 1 plus 1 is 0, and you carry the 1. 0 plus 1 plus carried 1 equals 0, and you carry another 1. 0 plus 1 plus carried 1 equals 0, and you carry another 1. And then 1 plus 0 plus carried 1 equals 0. But now you're able to carry that 1 over into the 5th bit. So if we're looking at this, it'll end up with 0001, 0000. And if we count these exponents, so that's 2 to the 0, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th. 2 to the 4th is 16. Which I usually just remember the order of the powers, like 1, 2, 4, 8, 16. So I know that's 16 right there. So the answer of 9 plus 7 is dependent on the size of your how many bits you have. Size of your data type, basically. So subtraction is like a little bit more difficult than standard subtraction that we learned in school doing binary. I think you could still do it the same way, but the way that the computer actually does it is using this thing called two's complement, which I never heard of until I got into college. It's a little bit confusing. There's like an actual technical definition. You can have a complement of any base number. I think I saw in my old textbook. So this is the textbook I use, Computer Engineering by Mano. This was like my first computer engineering book. Is a good starter, the first one that I used in college. And it goes into like base, the different base formats and everything. It goes into gates and everything else, Carnot maps, all that good stuff. So that's a good book to get. At least that's the one that I use. There may be better books out there, I don't know. But that's the first one that I used, and I thought it was a pretty good book as an introduction to number systems used in computers. So basically to get the two's complement, I just put like a really quick and dirty definition right here. This is not the technical definition of two's complement, but basically if you got a binary number and you got zeros and ones, you just swapped out the zeros for ones and ones for zeros. So you just basically flip everything. And then you add 1 to that. Don't ask why. It's a part of the formula. But if you I always think you just flip the zeros and ones and my number never does come out right. It's because you got to add an extra 1 at the end. So how this is useful to subtract one number from another number, you take the first number and then the number you want to subtract, you basically convert the second number that you want to subtract into 2's complement. You take the 2's complement of the number you want to subtract and then add those, then it's just addition again. And then you may have a 1 that you carry over again. You just drop off the 1 at the front of it. So here's two numbers, 8 and 5. So 8 is, and I'm just dealing with 4-bit numbers again. 1 0 0 0 minus 5. 5 is 0 1 0 1. So to get the 2's complement of 5, so 5 is 0 1 0 1. So to take the 2's complement of that, you flip the zeros and ones. So that gives us 1 0 1 0. Basically, you're taking the NOT. It's kind of like a NOT gate right there. You're doing the NOT of all the bits. So that gives us 1 0 1 0, but that's not the 2's complement. You got to add that 1 at the end. So that gives us 1 0 1 1. So to add 8 and 5, you take 1 0 0 0 plus the 2's complement of 5, which is 1 0 1 1. So add those. 0 1 is 1, 0 1 and 1, 0 and 0 is 0, then 1 and 1 is 0. Then you got the 1 at the front. So kind of like I was talking about overflowing. You got this extra 1 at the front, and you just drop that. So I just put an X right there. So you got 0 0 1 1, which is 3. So 8 minus 5 is 3. Here's another example, 14 minus 7. So 14 is 1 1 1 0. 7 is 0 1 1 1. So to take the 2's complement of 7, we're going to take 0 1 1 1, flip all the zeros and ones. So that's going to give us 1 0 0 0. Then we're going to add 1. So that's going to give us 1 0 0 1. So 14 minus 7. So 14 1 1 1 0 plus the 2's complement of 7, which is 1 0 0 1. Add those two together. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. And 1 plus 1 is 0. Then we got a 1 that we carry over, but since it's in the 5th bit position, we just forget about it. We just drop it. So 0 1 1 1 is 7. So 14 minus 7 gives us 7. So the last number system I want to talk about is hexadecimal. A lot of developers are probably familiar with hexadecimal, but I'm just trying to make an easy talk here, something easy. Maybe for anybody out there looking to get into computers and things like that, and aren't familiar with hexadecimal. So in base 10 in decimal, we got the numbers 0 through 9 for the first digit. In binary, we just have 0 and 1. But in hexadecimal, we have 16 different numbers. But numbers like 10 through 15, those are 2 digits. So we need a way in base 16 to represent those with only 1 character. So they just started using letters, A, B, C, D, E, and F. So I'm calling these digits again. I don't know if there's any specific hexadecimal nomenclature for a digit in hexadecimal. So I'm just calling it a digit. So basically, 1 digit in hexadecimal equals 4 bits in binary. So there's a direct correlation between hexadecimal and binary. So it's really easy to convert hexadecimal to binary. Easier than it was converting from like binary to decimal. So basically you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A. A is the equivalent of decimal 10. B is the equivalent of decimal 11. C is the equivalent of decimal 12. D is the equivalent of decimal 13 or 14. 13. E is the decimal equivalent of 14. And F is the hexadecimal equivalent of the decimal 15. So you'll see F a lot. You'll see like FF a lot, which is 255. Like if you're on an 8-bit system, FF is like all ones in binary, or 255 in decimal. So if you add 1 to FF and you got an 8-bit number, it's going to roll back over to 0. But yeah, a lot of times you'll see A for 10 and F for 15. A lot of the other ones sometimes you see like in a color code like a C0 or some combination of these hexadecimal numbers. Basically in your RGB, red, green, and blue, you'll see 2 digits for red, 2 hexadecimal digits for green, and 2 hexadecimal digits for blue. And that goes back to the really old web browsers before you had like named colors and stuff like that. All the colors in HTML were represented by hexadecimal. So a lot of times you'll see that carried over just because that's how the color codes were originally started. Or if you want to get really specific in a color code, instead of like typing all the binary equivalent, a lot of times it's faster just to put the hexadecimal in there. Yeah, so that's a 1-digit hexadecimal number, like I said, equals 4 binary bits. So F is equivalent to 1111. E is equivalent to 1110. So the next one I'm going to talk about or just mention is 2-digit, which I already mentioned a little bit previously, but 2-digit hexadecimal numbers, which are 8 bits. If you're working with 8-bit processors like the old NES and things like that, making old NES games, you'll probably see like this, or you'll see these codes especially like with memory addresses and things like that. So basically 00 is a decimal 0, 01 is decimal 1, 02 is decimal 2. Like I said, 0A is 10. All the way up to 0F is 15. Then you go to 10, which is 16. I think I have these on the next slide here. So yeah, I have them all listed out right here. So F is 15, which is 1111. So first column is hexadecimal. Second is decimal, base 10. Third column is binary. So you can see how it goes from 1 to F. And then doing the 2 digits just adds the digit in front. So I have the 1 in the first column. That's the 16 to the 0. Or 16 to the 1 value, and then the second column in red is the 16 to the 0 column, which is 1, so it's whatever that red digit is. So I have it all converted here. So like 1F is 31, or let's look at the 10 again. 10 in hexadecimal, that'll be 16 plus 0, which is 16. Then I have it in binary, 0001. And then 0000. I think I have more on this on the next slide, but like 20 is 16 times 2, which is 32, and 20, the 0 is just 0. So in binary, that's 0010, 0000. And like I said earlier, FF is 255, 1111, 1111. Oh, I didn't list those out. But yeah, basically, I'll go to the end here. Basically, the conversion is the same as the 10 to the 10 powers in the 2 powers, you're just dealing with 16 powers. I guess that's why I didn't list it out. Rarely you see 3 hexadecimal digits together. Maybe it's just because I'm familiar with like working with like NES games and things like that. I'm accustomed to seeing just 2 hexadecimal digits, which represents one 8-bit number. Go over a couple more examples. So like 80, that's 8 times 16 to the first, which is 128, plus 0 times 16 to the 0, which is 0 times 1, which is 0. So that's 128 plus 0. So that's going to give us, and it's really easy, like the first column in hexadecimal, that first hexadecimal digit, that translates directly to a binary number. And then the second hexadecimal digit, that translates directly into a binary number. So you just put those side by side. There really isn't any conversion, or not as much conversion from hexadecimal to binary. You just convert the first column to binary, convert the first hex digit to binary, convert the second column, second hexadecimal digit to binary, and that's your number. So converting from hexadecimal to binary is really easy, or vice versa. If you're going from binary, like let's look at like this one for 17. If you're converting from binary to hexadecimal, so you got 0001, so that's a 1. 0001, that's a 1. So that's just 1 1 in hexadecimal. Let's look at one more. So like this one right here, 1010 400000. So 1010 is A. That's 10. So that's A. Then 0000 is 0. So that's A0. So going to from hex to binary and binary to hex is relatively more simple than going to decimal. And I'll also mention, I didn't mention it earlier, but there is octal. In my 30 plus years of doing computer stuff, I've never really ran into octal. I think you might be able to use it. I think you can use it for chmod codes in Linux and things like that, but never really used octal that much. But octal is base 8, so it's basically the same thing. You just go from 0 to 8 or 0 to 7. But I've never really seen it much in use. So yeah, that's it for number systems. Hope people found it interesting. Maybe a nice refresher or a nice introduction for anyone who's never maybe heard of binary and hexadecimal, but never really understood exactly what they were or how to convert to those number systems. And yeah, basically it's because all computers are based on ones and zeros, trues and false. That's why we have to use binary and hexadecimal for a lot of things. So that's going to be it for Knox Game Design for November 2022. Appreciate everybody out there listening and watching.